12.2 kilometers. That is the deepest hole human beings have ever drilled into the Earth. It required 24 years of continuous effort, and the full engineering capacity of a Cold War superpower to reach that number. The planet's radius is 6,371 kilometers. That hole covers less than 0.2% of the distance to the center. We have mapped the surface of Mars in greater resolution than we understand what lies 50 kilometers beneath our feet. The geology of this planet, the hidden structure of Earth's crust, the underground mysteries that no instrument has ever directly measured, is more incomplete than most people are ever told. What is down there, and why? With everything modern science and technology can offer, can we still not reach it? That is the question this journey is built to answer. What's coming will shift how you see reality. Make sure you don't lose access. Hit subscribe. By the end of this journey, you will understand exactly why the most ambitious drilling project in human history was sealed shut and abandoned, and what it revealed before it stopped. You will understand why Earth's core runs hotter than the surface of the sun, and why that single fact determines whether liquid water can exist on any planet at all. The standard picture of Earth, solid, layered, stable, holds for the first 100 meters or so. After that, the physics change in ways that even the best engineering teams in the world failed to fully anticipate before they began drilling. This journey moves in 8 stages, surface to center, each one deeper and more extreme than the one before. At every stage, something contradicts the obvious assumption. Earth science tells us that the inner core of this planet rotates at a different speed than the ground you are standing on right now. Geoscience has not fully explained why. You have lived above this system your entire life. What follows will change how you think about the ground beneath you. The journey begins at the surface, not because the surface is simple, but because what the first few meters have already given us tells us exactly what we stand to gain by going deeper. In November of 1922, Howard Carter pressed a candle through a breach in a sealed doorway in the Valley of the Kings and looked into a chamber that had not been opened in 3,200 years. What he saw, he later described in his field notes as wonderful things gold, statues, furniture, the entire intact inventory of a royal afterlife. Tutankhamun's tomb sat less than 8 meters below the desert surface. 8 meters, a depth a motivated person could reach in an afternoon with basic tools. What made that preservation possible was not magic or accident. It was geology. The limestone bedrock, the mineral composition of Earth's crust at that precise location, the near-total absence of groundwater moisture, all of these combined into a natural vault that no human-built archive has ever equaled. The Earth at shallow depth does not merely hold what we bury. It holds it unchanged, across spans of time that dwarf any institution we have ever created. This is not isolated to Egypt. Across the world, the first few meters of soil function as the most extensive archive in human history, preserving isotopic climate records, dormant microbial communities, seeds viable after centuries, and artifacts from every civilization that has ever existed. The ground preserves because its mineralogical properties create conditions of stability that the surface above it cannot match. But humans have used the near surface as more than a vault. They have used it as armor. In the Siu Chi district, north of what is now Ho Chi Minh City, fighters during the 1960s and 1970s constructed and maintained a tunnel network stretching more than 250 kilometers, corridors, sleeping quarters, field hospitals, weapons caches, all carved at depths of 3 to 8 meters. The system was invisible from above. It withstood sustained aerial bombardment and chemical fumigation. At its operational peak, it functioned as an underground city with a population exceeding 10,000 people. At the same time, on the other side of the Cold War, governments on both sides were commissioning classified bunker complexes designed to survive nuclear detonations, placed at specific depths, calculated to attenuate blast pressure and thermal radiation. The density of the Earth itself, the physics of what solid rock does to a shockwave, was the protection. A pharaoh's tomb and a command bunker, separated by 3,000 years and 10,000 miles. Operating on the same fundamental insight: go deep enough and the planet becomes your shield. But shielding requires depth. And the moment you attempt to go beyond a few dozen meters, you discover that the Earth is not a passive partner in the arrangement. It has its own terms. Before any machine attempted to go deep, biology already had. In 1997, researchers investigating root systems in the southwestern United States traced the underground extent of a wild fig tree, an unremarkable specimen by any surface measure, and found its roots descending to a depth of 120 meters. 120 meters. That is roughly the height of a 40-story building, inverted underground, drawing moisture from aquifers that no surface observation would have revealed. No drill bits, no engineering budget, no refrigeration systems. Just slow, patient biological chemistry, following the path that physics allowed, across decades. This benchmark matters because it places human engineering in an unexpected context. The Arsenalna station of the Kyiv metro in Ukraine, the deepest subway station on Earth, descends to a platform, depth of 105.5 meters below street level. Reaching the platform from the surface requires approximately 5 minutes on one of the longest escalator runs in the world. By any standard of civil engineering, it is a significant achievement. By comparison to that fig tree, it is shallower. The irony here is precise. The boundary between what biology achieves through patient chemistry and what human engineering achieves through industrial force is narrower than instinct suggests. Nature outruns us at our own best depth and then stops. Below the reach of roots and microbes and urban construction, conditions change in ways that biology cannot accommodate and engineering can only partially manage. The place where that change becomes most physically real for any human being is a mine. The Mponeng gold mine, southwest of Johannesburg, South Africa, is the deepest active mine on Earth. Its lowest working levels descend to approximately 4 kilometers below the surface, roughly the cruising altitude of a small propeller aircraft, but directed straight down into the rock. At that depth, ambient rock temperature reaches 66 degrees Celsius. That is 150 degrees Fahrenheit. Without intervention, those conditions make sustained human work physiologically impossible within minutes. To keep the workforce functional, the mine continuously pumps ice slurry, a mixture of ice and water produced on the surface, and piped through insulated conduits into the working levels. Even with this system in operation, temperatures at the rock face hover around 28 degrees Celsius. The atmospheric pressure at that depth causes rock to fracture spontaneously, a phenomenon called a rock burst, releasing stored elastic energy in an instant with the force of a localized explosion. Mponeng employs continuous seismic monitoring specifically to anticipate these events before they occur. Workers descend to those levels by cage elevator, a journey that takes nearly an hour each way. Their time underground is regulated by strict physiological limits. The economics that make this operation viable are striking. Mponeng's ore contains approximately 8 to 10 grams of gold per ton of rock. To yield a quantity of gold roughly equal to a standard wedding band, miners must excavate, process, and dispose of nearly 100 kilograms of ore. At 4 kilometers, in those conditions, the Witwatersrand Basin, the geological formation that makes Mponeng possible, is approximately 2.7 billion years old. The gold it contains was deposited by rivers that no longer exist, draining a landscape that bore no resemblance to modern Africa. The mine's workforce is, in a precise sense, extracting the mineral record of a vanished world. 4 kilometers is 0.06% of the distance to Earth's center. If reaching 4 kilometers requires refrigeration systems, seismic monitoring, and an hour-long elevator descent, what happens when you try to go 3 times deeper, not with human workers, but with a drill? In 1970, Soviet scientists began drilling on the Kola Peninsula in the remote northwest of Russia. The objective was explicit and stated from the beginning: to reach the Moharovishchik discontinuity, the geological boundary between Earth's crust and the mantle below it, and to study what conditions existed there. It was not a commercial operation. It was a scientific project of the same order of ambition as the space program, built on the conviction that understanding what lies beneath the surface was worth whatever the effort required. For 24 years, the drill descended. By 1989, it had reached 12,262 meters. No drill has gone deeper since. Then it stopped. Not because funding collapsed, though that became a factor later. Not because the equipment failed in any conventional sense. It stopped because the Earth itself stopped cooperating in the way the engineers had assumed it would. The models the Kohler team had built predicted rock temperatures at that depth of approximately 100 degrees Celsius, challenging, but manageable with available technology. What they measured was 180 degrees Celsius. That discrepancy of 80 degrees did not merely present a thermal problem. At those temperatures, the rock surrounding the borehole did not behave as solid matter. It behaved plastically, flowing slowly, continuously, inward toward the empty column of the hole. The drill would descend, and the walls behind it would close. Sections of drill string became permanently embedded in material that refused to hold its shape. The borehole was not breaking the rock was absorbing it. The Kohler team also made discoveries that had nothing to do with temperature. At depths where models had predicted dry, dense, compressed crystalline rock, they found free water moving through microscopic fractures in material that theory had classified as impermeable for billions of years. They found microscopic fossils of marine microorganisms at depths where no geological model had placed biological material. And they found that the boundary between granite and basalt, assumed to mark a transition between different rock types, was in fact thermal, the same rock, behaving differently under different conditions of temperature and pressure. Nearly every assumption the project carried into the ground in 1970 turned out to be wrong in some important and specific way. The Kohler Superdeep borehole was officially terminated in 1992. Today, the hole is sealed with a bolted metal cap on a largely unmaintained site on the peninsula. The equipment around it has rusted. The facility is abandoned. The hole itself, the deepest penetration humanity has ever made into this planet, is 23 centimeters in diameter. The width of a dinner plate, 12 kilometers deep. If you were to represent Earth as a standard globe 30 centimeters across, the Kohler borehole at that scale would be less than half a millimeter deep. A light scratch on the surface of a billiard ball, scaled against the planet. The sum total of our drilling is not even a skin-deep wound. But the most unsettling part of this journey is still ahead, because what lies below that point where the Kohler drill stopped is not simply rock behaving strangely. It is something of a fundamentally different nature. Most people, if asked to describe what exists beneath Earth's crust, would say magma, a vast underground ocean of liquid rock held at bay by the solid ground above it. That image is intuitive. It is also wrong. The mantle, the layer that begins roughly where the Kohler drill stopped and extends downward for nearly 2,900 kilometers, is not liquid. At the pressures that exist within Earth's mantle, rock does not melt. It compresses into a state of extraordinary rigidity, and yet it flows. This is not a contradiction. It is a matter of timescale. The mantle is solid on any scale relevant to human experience. It does not move during an earthquake, or a century of observation, or 1,000 years of recorded history. But on geological time, measured in millions of years, it undergoes viscous flow, the same fundamental process by which glass very slowly deforms over centuries. Applied here at a scale that makes any ordinary comparison inadequate. Earth's mantle accounts for approximately 84% of the planet's total volume. Heat, rising from the deeper interior drives convection currents within it, slow, continent-scale circulation patterns that move sections of rock upward, laterally, and back downward over tens of millions of years. These currents are the direct engine of plate tectonics. Continents do not drift because something pushes them from behind. They move because the mantle beneath them is in slow, continuous motion, and the surface plates are carried along with it. Volcanoes are not holes in the crust through which magma escapes. They are primarily the surface expression of mantle plumes, columns of unusually hot rock rising from depth, carrying enough thermal energy to partially melt the base of the crust above them. The Hawaiian island chain is the preserved surface record of a single mantle plume that the Pacific Plate has been drifting over for approximately 70 million years. Each island in the chain represents a different point in time. The oldest, eroded now below the ocean's surface to the northwest, are furthest from the active plume. The Big Island, still volcanically active today, sits directly above it. The heat driving all of this has been escaping from Earth's interior since the planet's formation, approximately 4.5 billion years ago. The Atlantic Ocean is widening, at approximately the rate your fingernails grow, invisible within a human lifetime, immense across geological time. Every earthquake you have ever felt, every volcanic eruption you have ever seen documented, is surface evidence of this deeper process. What drives the mantle's motion comes from something far stranger than the mantle itself. Below the mantle, at approximately 2,900 kilometers of depth, begins the outer core, and it is the reason life exists on this planet's surface. The outer core is composed primarily of liquid iron and nickel, approximately 2,200 kilometers thick. Convection currents within this liquid metal generate electrical currents, and those currents produce Earth's magnetic field, the invisible protective shell that extends tens of thousands of kilometers into space, continuously deflecting the solar wind that streams outward from the sun. Without that magnetic field, the solar wind would gradually erode Earth's atmosphere. This is precisely what happened to Mars. Mars lost its magnetic field approximately 4 billion years ago, most likely because its smaller core cooled and solidified. The Martian atmosphere subsequently stripped away to less than 1% of Earth's surface pressure. The result is a planet with no liquid water, no breathable air, and no life that any instrument has yet detected. Earth's magnetic field is not background scenery. It is an active, ongoing precondition for the existence of everything living above it. The field is also not fixed. Magnetic north migrates measurably. It has shifted hundreds of kilometers since systematic observation began in the 19th century. The field also reverses its polarity on timescales averaging between 200,000 and 300,000 years. The last full reversal occurred approximately 780,000 years ago, meaning we are statistically past the average interval. During reversals, the field weakens substantially before rebuilding in the opposite orientation. What a substantially weakened magnetic field would mean for modern electronic and communications. Infrastructure remains an active and unresolved area of research. At the center of the outer core sits the inner core, a solid sphere of iron, approximately 1,220 kilometers in radius. Comparable in size to the Moon. Its temperature is estimated at approximately 6,000 degrees Celsius, comparable to the surface of the Sun. It remains solid not because it is cold, but because the pressure at Earth's center, approximately 3.6 million times atmospheric pressure at sea level, prevents iron from liquefying, regardless of temperature. Pressure, not cold, holds the innermost part of this planet in a solid state, and the inner core rotates independently. Seismological data, using the waves generated by earthquakes that travel through the core as a form of deep planetary imaging, indicates that the inner core rotates approximately 0.3 to 0.5 degrees per year, faster than the surface above it. The leading hypothesis involves electromagnetic coupling. The magnetic field generated by the outer core exerts a rotational force on the inner core, accelerating its spin fractionally. Studies published in 2023 suggests this differential rotation may itself oscillate over multi-decade cycles, adding a layer of complexity to a system already operating entirely beyond direct observation. Earth's inner core is not a static endpoint at the bottom of a diagram. It is a dynamic, still evolving structure, and we understand its behavior entirely through the echoes of distant earthquakes reaching instruments on the surface. What this journey reveals is not a collection of separate curiosities. It is a single argument from the 8 meters that preserved Tutankhamun's burial chamber for 3,000 years, to the 12 kilometers where Soviet engineers encountered physics they had not predicted, to the 2,900 kilometers where liquid iron generates the field without which this planet could not sustain a single living cell. Earth is not a backdrop to the story of life on its surface. It is a system in continuous motion, operating across timescales and at conditions that lie entirely outside human experience. The limits we encountered at every stage were not failures. They were precise measurements, data points that tell us exactly where human scale ends and planetary scale begins. That boundary, it turns out, is closer to the surface than most of us had ever thought to ask. Somewhere beneath you right now, at a depth no instrument has directly reached. Through layers no drill will touch in this century, iron is crystallizing in silence. The temperature surrounding it exceeds the surface of the sun. The pressure there would reduce any material we can name to a state we could barely recognize. And this has been continuous, uninterrupted, since before the first living cell appeared in the shallow water above it. We live on the skin of something we have never seen.